In this presentation, I'm going to go over the Unit 3, Section 2 notes for covalent bonding. We have four objectives for this set of notes. First is why do bonds form in general? We'll talk about the energy of atoms. Specifically, in Section 2, we'll focus on covalent bonds and Lewis dot structures, which show the two-dimensional arrangement of atoms in a molecule. In number 3, we'll talk about the types of covalent bonds. Specifically, we'll talk about multiple covalent bonds and what we call them. And in the final section, section 4, we'll talk about how to build covalent molecules, more specifically Lewis dot diagrams. And we'll also go over that in a later video in more detail. So first, let's talk about why bonds form. And this is all going to have to do with energy. You'll be saying this word energy a lot. Really what this is referring to is something similar to how you think of it, how like kinetic atoms are, how much they're moving, but it's also about how stable they are. Low energy usually meaning stable and high energy meaning unstable. So specifically, atoms and in general chemistry usually act in ways that try to lower the energy of a system. They try to lower their overall energy. Specifically, if I look at atoms like calcium and oxygen in this case, they're going to form ions that we saw in a previous unit because it lowers their overall energy. They don't have full octets around them, and to lower their energy, they either lose or gain electrons. So ionic bonding also is all about lowering energy. We actually saw this in an earlier unit as well, where when electrons dropped down energy levels and let off light, they were lowering their energy. They were going from an unstable high energy position to a more stable lower energy position and letting off light. So what does this have to do with covalent bonding? Well, one of the general principles in chemistry is that opposite charges attract and similar charges repel. If we think about one atom, we can see that negative electrons are attracted to the positive protons which are in the nucleus. When we bring another atom close to our first, we have an interesting situation where electrons on one atom are attracted to both their own nucleus and the nucleus of their neighbor. So, to lower their overall energy to get to the spot where they want to be, they're going to have to exist somewhere between the two atoms. And specifically, we can look at energy in terms of the force of repulsion between two atoms and the force of attraction. If we have two atoms and we keep them somewhat far apart, the electrons in this like electron cloud around each nucleus, they're kind of too far away to see or to feel the effect of the opposite positive nucleus. As we bring those atoms together, the nuclei will basically repel one another, but the electrons in each atom are going to be attracted to the opposite nucleus, which is positive, because again, their charges are opposite, negative for the electrons and positive for the protons. That attraction will bring those atoms together, and they'll reach some distance where the electrons pulling the atoms together and the positive nuclei pushing themselves apart will get to the point where those forces are equal and the energy is minimized. And this is really the situation right here where we have a covalent bond. When the electrons pulling the two nuclei together is offset by the nuclei pushing each other apart. Now, if we smushed these two atoms together, the electrons would still technically be attracted to the opposite nucleus. You can see that with these little blue arrows here. But those protons, the nuclei, would be so close together they'd push apart like magnets. So they would end up repelling each other and end up back at this third, very stable state, where again, the energy is minimized. We're actually not going to deal with this level of sophistication going forward. Just know that there's some distance where that energy is minimized and we have a covalent bond. Medium energy to start, high energy when these are far apart, lowest energy when they're closest together in that covalent bond, and high energy again when they're smushed together. So, quick question about energy. If I try to shove these two oxygen ions together, they're both -2, will they be in a high energy or state or a low energy state? Take your guess. And if you said high energy state because the similar charges repel, You would be correct. Similar charges, if you try to push them together, they're going to want to repel, so they'd be in a high energy state. They want to become more low energy. Now let's talk about covalent bonds and Lewis structures. Covalent bonding, like we said, is when those atoms are close together. It's this low energy state where the attractive forces of the electrons being attracted to each nucleus and the repulsive forces between the two nuclei, where those forces are balanced and the electrons between them are shared. We call that a covalent bond. Really, in brief, it's when electrons are shared, that's when we call covalent bonding. Now, covalent bonding helps to lower the energy of an atom because it fills the octet rule. It says that an atom must have a full valence shell. If I take these three atoms, notice that hydrogen, one of our exceptions to the octet rule, it's filled when it has 2 electrons. Carbon, it looks like it needs 4 more electrons to fill its valence shell. And this sulfur atom on the right, it needs 2 more electrons to fill its valence shell. So covalent bonding allows these kind of spots in each of these atoms, these white circles, to be filled. But instead of gaining or losing electrons like we did with ionic bonds, covalent bonds are going to be formed again when 2 atoms share their single electrons. For instance, if I take these 2 hydrogen atoms, they both have 1 electron, but they want 1 more to fill their outer shell. So they'll take both of their single electrons and put them in the space between the 2 atoms, kind of like we see on the right. This is going to be our covalent bond. We have the 2 atoms kind of felt by the hydrogen on the left, and those 2 electrons are also felt by the hydrogen on the right. So they've sort of both filled the octet rule. However, in covalent bonding, we don't show those 2 electrons between the 2 atoms to show that they're bonding with each other. We just draw a line between the 2 hydrogens, and that line represents the 2 shared electrons. So quick question, how can we predict how many bonds each atom will need to form in order to have that filled outer shell? Well, really, the amount of bonds is just going to be equal to the number of single electrons. This hydrogen will make 1 bond to get a full outer shell. This carbon will make 4 bonds to get a full outer shell. And this sulfur, because it has 2 single electrons, it should end up with 2 single bonds. But let's jump into Lewis structures. The Lewis structure of an atom, it tells us exactly how many bonds of the atom will form. Just like we said before, the number of single electrons shows the number of bonds. Halogens are group 17 elements, such as chlorine on the bottom here. They have 7 valence electrons, and they'll form 1 covalent bond because they have 1 single electron. Hydrogen is also an example. It's not a halogen, but because it has 1 single electron, it'll form 1 covalent bond. Chalcogens, or more commonly known as the group 16 elements, these have 6 valence electrons. And if we look at oxygen as an example, we can see that because it has 2 single electrons, it'll form 2 single bonds. Pnictogens, or the group 15 elements, such as nitrogen and phosphorus, 3 single electrons each, so they'll form 3 covalent bonds. And the carbon group, because each of these atoms, such as carbon and silicon, because they have 4 single electrons, they will form 4 covalent bonds. So what are the different types of covalent bonds? This section is both simple and a little difficult at the same time. Single bonds, we also call sigma bonds. The reason is that that first bond, known as the sigma bond, it's kind of different than the other bonds afterwards. That first bond is sort of the strongest of the bonds, and it's directly between our 2 atoms. It's pretty simple. Just 2 electrons shared directly between 2 atoms' nuclei. And you can call that a sigma bond by writing it out, or show the symbol sigma underneath the bond. Double bonds, these are a little bit different. We can have atoms between one another form 2 bonds. For instance, check out these 2 oxygens. If they're going to bond together, they're going to do so twice. They'll share 2 sets of single electrons. And usually we rewrite that to show those bonds as similar lengths. The first bond formed is still that regular old sigma bond, But the second bond we call a pi bond. So in a double bond, we have one sigma bond, and the second bond is a pi bond. Pi bonds are not quite as strong as sigma bonds, and they're more on the outside of an atom. We can also have a triple bond, but luckily this follows the similar kind of pattern. The first bond is going to be the sigma bond, and the remaining two are both pi bonds. So if I look at an example of nitrogen, which bonds to itself with a triple bond, the two on the outside we could call the pi bonds, and the one in the center would be that sigma bond. A better image of this would be if you see these two carbon atoms here in the center. We can see that sigma bond is directly between them, those two electrons shared directly between the carbons. And those pi bonds are around the outside. They still connect the carbons. There's still two electrons each, but they're kind of on the outside of those carbons. So, quick question. There are no such things as quadruple bonds, such as I have shown between these carbons. Why would this situation be difficult? What would be high about the energy of all these electrons? Go ahead and take a guess. Pause your video if you need to. Consider the fact that this is high energy because these bonds each have two electrons. So to put them all directly between the carbons would be shoving too many negative charges in the space between two atoms, and those negative charges would repel one another. Just so happens that when we have 4 bonds worth of electrons between two atoms, it's too repulsive of a force. Real quickly, as a side note, we're going to talk about diatomic molecules. Certain elements in certain atoms form diatomic molecules because they naturally form in pairs because of covalent bonding. If I look at hydrogen and my 4 halogens, fluorine, chlorine, bromine, and iodine, these form stable molecules where they have a single bond between two atoms and no other spots to bond. We can also look at examples like oxygen, which forms a double bond and is stable between two oxygens, and nitrogen, which can also triple bond to itself and is stable bonded to itself. So in nature, whenever we encounter these elements by themselves or as pure elements, they always occur as pairs of atoms because those are their stable or low energy covalent structures. Lastly, let's look at the steps to building a covalent molecule. The process is fairly straightforward. We'll want to draw Lewis dot structures for each of the atoms in the molecule. I have CH3Br here. First thing to do would be draw the valence structures for all 5 of these atoms. Next, we want to rearrange our pieces so that the element with the most number of single electrons is in the middle. In this case, I can see the carbon has my most single electrons. So I will rearrange this so that carbon is in the center and the other atoms are around the outside. Next, I'm going to rearrange those Lewis dot structures so the single electrons face one another. I can see that this bromine and this carbon already are facing their single electrons, as are the carbon and the hydrogen at the bottom. But for these 2 hydrogens on the top and the left, I'll just rearrange their Lewis structures so their single electrons face the carbon. And finally, we want to connect these single electrons by drawing lines between the atoms. And we'll replace those single electrons with the lines. Don't forget that those lines each represent 2 electrons. One more rule. In some cases, it might be difficult to decide which atom goes in the center. In this case, we have hydrogen, carbon, and nitrogen. Notice that nitrogen can form 3 bonds and carbon can form 4. We will always go with that most amount of single electrons, but we'll find that sometimes it's hard to decide which. In that case, we choose the atom with the lower electronegativity. That would be carbon in this case, as compared to nitrogen. Notice that hydrogen, even though it has the lowest electronegativity, it can't go in the center because it can only form 1 bond. If it went in the center, it couldn't bond to multiple atoms. And one more rule. Molecules can technically have multiple central atoms. We'll look at this more in the next video. But if I try to make this molecule here, we'll notice that there are technically 2 center atoms, both of our carbons. And you'll end up having to play around with Lewis structures a bit to find the format that actually works. And that is it for Lewis dot structures.